and gentlemen, we're going to get started on statics, Hibbeler statics. Going to go through the basics first. Numbers, units, things like that. Fundamental quantities, length, time, mass, current. Current we won't have to worry about. That's electrical current. Derived quantities, force is mass times acceleration. Acceleration is distance, length, divided by time squared. Pressure is force per area. Velocity is length per time, and so on. So idealizations, I didn't want to flip that quite that fast. Idealizations, a particle. A small body is infinitely concentrated, which is not really true. But to a good approximation it is. Rigid bodies, a collection of particles whose position is fixed relative to other particles. But even seemingly solid bodies may deform even if a tiny bit, maybe by 1/10%, a close enough approximation for us to do our statics work. Concentrated forces. Forces are distributed, even if they might be to a fraction of a millimeter, like a pinpoint. But we approximate them as concentrated. These approximations work. Here's a joke. Mathematician and physicist and engineer were asked to answer the question. A group of boys are on one wall of a dance hall, a group of girls on the other. Both groups were instructed to advance each other by 1/4 the distance separating them every 10 seconds. So at 10 seconds, they'd be half the distance. At 20 seconds, they'd be 1/4, and so forth, because they're both advancing 1/4. When did they meet in the center? Mathematicians said they'd never meet because the series is infinite. The physicist said they would meet when time equals infinity. The engineer says that within 1 minute they would be close enough for all practical purposes. Reality is always going to deviate from our models. Even the physicist or the mathematician who comes up with these incredibly elegant, fast, smart models, there's going to be some errors in it because their model doesn't account for everything that reality can throw at it. So here's another way to look at units now. So here we have the quantities on one side, the units on the other, SI or MKSA, Standard International, that's what SI stands for, which is the meter, kilogram, second, ampere unit system. I wish they'd keep calling it MKSA because it reminds us what the fundamental units in this system are: the meter, the second, the kilogram, and the ampere. I love acronyms. FPS, foot-pound second. The ampere for electrical current is the same in both because electrical work was figured out after the metric system was invented. So electricity became metric automatically. Force, newtons in the MKSA or the SI system, pound in the foot-pound second system. Pressure, Newton per meter squared or a Pascal in the SI system, pounds per square inch, PSI, or pounds per square foot, and so forth. Keep going. Unit of measurement, conversion factors. Here's a few conversion factors between forces, mass, and length. Mass in the foot-pound second system is a slug. It's called a slug. Okay. Newton's first law, equilibrium, that an object will accelerate. It'll either be at rest or it'll move with constant motion. That means constant velocity. Unless the forces are not zero. If the sum of these three forces is zero, it'll either be at rest or move with constant velocity. That's what we mean by equilibrium. Second law, force equals mass times acceleration. Third law, the force one body exerts on another, A exerts on B, is equal and opposite to the force of B on A. That's what's action-reaction. And we need to be careful about this, because when we're doing a free body diagram, we are talking about the forces acting on one body. We got to be careful that we don't put down a force of A on B when we do that, when we draw free body diagrams. That we're only looking at the forces acting on A, and that would be the force of B on A and other forces. Okay, law of gravity. So this is the big fat law, which we never use, because Earth's surface has a radius of 6,380 plus or minus 10 kilometers. From the bottom of the deepest parts of the ocean is about 10 kilometers less than this, and the top of the highest mountain is about 10 kilometers bigger than this. So you can see that's plus or minus 1 in the third digit. In other words, it will not affect this quantity much. Little g is the acceleration of gravity times the mass of the Earth divided by the radius of the Earth squared. Everywhere on the surface of the Earth, it's approximately 9.81. That is what we will use in this textbook, in all homework, exams, and so forth. That is what we will use for the acceleration due to gravity. And then you can figure this out yourself, what little g is from the mass of the Earth, big G, and the radius. So use 9.81. If you're in the FPS system, 32.2 feet per second squared. Weight is going to be mass times the acceleration due to gravity. Prefixes in the metric system. They're all powers of 3. 10 to the third, 10 to the sixth, 10 to the ninth. Giga means a number times 10 to the ninth. Mega means a number times 10 to the sixth, and so on. Submultiples, milli, 10 to the negative 3, micro, 10 to the negative 6. It uses the Greek letter mu, which is going to be hard on Canvas, by the way, so write the full word micro out. Nano, 10 to the negative 9th. Separate units by a dot or enclosed by parentheses if there might be confusion. Exponents refer to both the prefix and unit. So millimeter squared means enclose the unit millimeter and then square it. So that would be 10 to the negative 6th meters squared, not 10 to the negative 3 meters squared. Okay, prefixes should be in the numerator only. In other words, if you have a fraction, newtons per millimeter, we should write it as kilonewtons per meter. Keep numbers between a tenth and 1,000 if possible, and use the appropriate prefix. Okay, so ways to express our numbers that are easily readable by others. That's the whole point of this. Make sure dimensions on both sides of an equal sign match. So distance equals velocity times time plus 1/2 at squared. Well, the distance in meters is meters per second times the time, seconds. Is that true? Yes. The times will cancel out. So the seconds, ooh, that's too big. I didn't want to do it quite that big. Let's do that. Seconds will cancel out. Seconds squared in this case. 1/2 a, here's a, and here's t squared. That will cancel out. Okay. Keep answers to at least 3 sig figs. You may keep more if you wish. Rounding to 3 significant figures. If the fourth significant figure, I'm giving the example of 3 significant figures. If it's 4 significant figures, then this would be 5, and so on. If the fourth figure is 5 or greater, increase the third significant figure by 1. If the fourth significant figure is less than 5, leave the third significant figure alone. and increase the third. Oops, this is a mistake. There we go. Cross this guy out. And I need a 5 here. Less than 5. Give myself an editing mark. There we go. Store intermediate results in your calculator or computer, and that should be OR. Okay. So that means in the memory of your calculator or computer or Excel spreadsheet or whatever. Because rounding, if you don't, you'll have rounding errors that compound. They'll get bigger and bigger and bigger and bigger, so that your answer significantly deviates from 3 significant figures of the correct answer. So you want to store those intermediate results in your calculator. Use the memory of your calculator or computer. I like Excel myself. Okay. Problem solving. Make a sketch. Organize your known and unknown quantities and assign a variable to the numbers. We don't use numbers, we use variables. And then we plug the numbers back into the variables to evaluate at the very end. S-O-L-V-E, S-O-L-V-E, solve method. List possible equations. If an equation doesn't apply, if you figure that out later, just cross it off. You're trying to brainstorm in this step. Vary the equations to get your unknown variable on one side and everything else on the other, and then evaluate. Plug and chug. Do the calculations. Make sure they make sense. Here's a YouTube video on solve that goes through the process. Okay, that's it for Chapter 1. We'll end here, and I will pick up with Chapter 2.